get through whatever we need to today. Okay. Oh, by the way, now that we're into February, I should give you a heads up at the end of this month. So the very end of February, very beginning of March, I'm going to be away at a conference in Amsterdam. So what I will do for the 2 class meetings that we'll have during that week is I'm going to pre-record lectures done, so that'll be made available in Canvas before I go. But certainly you can, I'll still be accessible by whatever messaging you prefer to answer questions and so forth.
You said that last week of February?
Yeah, so February, let's see, 6, I think it's February 27th, and I'm gonna pull up a calendar to make sure. Monday, Wednesday, yeah, February 27th and March 1st are the 2 days where I won't be here. Yeah. And a week before that, it's gonna be Mardi Gras break, so we'd only meet on a Wednesday, so I won't be seeing much of you during that time, but that stretch. Okay. Now, last time introduced to you what is a series, and focused mainly on geometric series, which is possible to determine not only whether it converges or not, but also what is the sum of a geometric series when it does converge. So now we're going to look at another kind of series, which is possible to figure out what sum is, in addition to answering the question of convergence. And that is called a telescoping series. All right. Now, I'll start off with an example. From 1 to infinity of 1 over n minus 1 over n plus 1. So this entire expression is, when you substitute n equal 1, n equal 2, n equal 3, is going to be summed up. Now, we get an idea as to what's going on in a series by writing out the first few terms. So if I start with n equal 1, I would get 1 minus 1 over 1 plus 1, so 1/2. I'll put in parentheses. So this is what we get for n equal to 1. And then I'm going to continue with n equal 2. What will I get? 1/2 minus 1/3. Okay. Then what? Keep going.
1/3 minus 5.
Okay, and I imagine you can see the pattern by now. I'll write out a few more. Feel like going. Okay. Actually, I'll stop there if it's a 5, not an S. And so on. Okay. Looking at these numbers, can you tell me how this can be simplified? Yeah.
Like the second term of one of the parentheses cancels out with the first term of the next one.
Yeah, so this minus 1/2 cancels out with this plus 1/2. This minus 1/3 cancels out with this plus 1/3. Cancellation all over the place. In fact, almost everything I've written here goes away. The only thing it doesn't, okay, so this is n equal 4, n equal 5. Whoops, that's anyway, 4. Not sure what happened there. Okay, so what that means is a partial sum is relatively easy to figure out because, okay, you can write out a partial sum, but almost everything in that partial sum cancels.
Wait. Isn't that, shouldn't any-
Yeah, yes. Sorry,
I was like,
I think because I had the 5 there, it's, okay. You'll have to check me. Everyone's at UC Irvine, my first teaching job post PhD. And what I would hear about some of my colleagues in the math department is that like a student would do what you just did, point out an actual mistake. And then the instructor would be like, no, I didn't make a mistake, you know, just to totally deny it. It's like, okay. So if I call the definition of a partial sum. Okay, now I'm going to refer to this expression we're adding up as an as usual. So if I let Sn be a1 plus a2 up to an, in the nth partial sum. Now, to refresh your memory from last time, partial sums are essential because a series converges if and only if the sequence of partial sums converges. So what we have here is the sum of a1, a2, a3, a4. So we could say that the 4th partial sum is equal to whatever didn't cancel. So 1 minus 1/5 or 4/5. Okay. Questions so far? Yeah. What if I went out one term more? So I'd want the next partial sum, S5. So what would happen if I were to do that?
1 minus 1/6.
Yeah, so I would add on 1/5 minus 1/5. This is normally today. 1/5 minus 1/6. So the 1/5 would cancel with its minus 1/5. The minus 1/6 would still be there, and the 1 would still be there.
So you simplify it to n minus 1 over n.
Actually, that, well, almost. So Sn would be equal to n over n plus 1.
Oh, yeah.
Okay,
Wait, you couldn't. Yeah, I mean, it was the same thing, it's just,
yeah, you're all shifted, yeah. Okay, so what happens to this as n goes to infinity?
Right, it approaches 1.
Yes, yes. So this sequence of partial sums converges. The 1 as n goes to infinity. So we can conclude that this telescoping series converges to 1. So the idea is you write out some terms, and it's a telescope. We call it telescoping series because of the cancellation that happens between terms. So you look at what doesn't cancel to figure out what the partial sum must be, and now you look at that sequence of partial sums. Does it converge? And we see that in this case it does. Any questions on this one before I do another?
I just want to explain. So how did we, I understood everything up till we went from S5 to S.
Okay, so looking at the pattern,
Mhm.
see, okay, so S4 has to be 4/5, S5, 5/6. So whatever value of n we had here, that showed up in the numerator,
Oh, okay,
and then that +1 in the denominator.
thank you.
Third question? Okay. Okay, next one. We have. Infinity 1/n times n plus 2. Now, for this one, it doesn't have the same appearance as the first one in terms of telescopic series where you have a lot of cancellation. If I were to write out the first few terms, we have 1/1 times 3 plus 1/2 times 4, so on. But there's no clear way to have cancellation between terms because it's not written in the right form for that. We'd like to have it written as something like this, where you can write out terms and cancel things. So what can we do with that to get it into a form like the previous example? Partial fractions. And how many of you think you remember how to do partial fractions? Okay, yeah, that's the likely response. So, okay, and that's fine because I will refresh your memory as to how to do partial fractions. Okay. We need to decompose this. In a way that we can see the telescoping effect. So the idea is, so in this example, we want to write this fraction in a certain form involving simpler fractions. That's where the name partial fractions comes from. Fractions involving only part of the denominator instead of the whole thing. So here we have these factors, n and n plus 2. So we want this to be in the form a over n plus b over n plus 2, where the constants a and b have to be determinants. Okay. So anytime you have a denominator consisting of distinct linear factors like this n and n plus 2, you can break it down to a sum where you have each one of those factors, only one of those factors in each denominator, and that's a constant in the numerator. There are other partial fraction scenarios that would have been covered in Cal 2. We're not going there today. And it wouldn't be helpful for telescoping series anyway. Okay. And notice I just magically say what the result is, but I'm gonna refresh your memories to how to get it right here. So, or those of you who remember partial fractions better can help out. Starting with this form, does anyone know what is the next step?
Oh, that's one.
Yeah, multiply both sides by the denominator of the original fraction. So you can multiply both sides by n and n plus 2, thus canceling with denominator on the left side. And then on the right side, if I multiply by both n and n plus 2, we're going to have one factor cancel in each case. So whatever this is not over shows up here with the a. So a times n plus 2. And then here we multiply by n and n plus 2, the n plus 2's cancel. So whatever isn't underneath it goes up here. So now we have this equation that we want to solve for a and b. You don't remember what happens next?
Yeah, so we need to, yeah,
Plug in numbers.
we need to isolate one of them and then plug that into the next one.
So
any
it's like
close
plugging
to
in zero.
-2.
For them, solve for A.
Yeah. What were you gonna say? Oh, else we covered, okay. Okay, if you choose any two, we need two constants. We have two constants to find. So we need a system of two equations and two unknowns. if you were to select any two distinct values of n to substitute in here, you would get a system of two linear equations that you can solve. But some values of n are more convenient than others, and that's what some of you have said. If you substitute a value of n that makes either one of these factors 0, then you can solve for a and b much more easily. It's called the method of creating zeros, as calculus textbooks like to refer to it. So start with setting n equals 0. So that'll cause this term to disappear. I'll get 1 equals 2 times a. So now that immediately reveals the value of a as 1/2. And then you substitute n equal to -2. That will leave this, cause this factor to go away. So then you'd have 1 is equal to b times -2. So b is equal to -1/2. So the result is that 1 over n plus 2 is equal to 1/2 over n minus 1/2 over n plus 2.
That looks much better.
Okay. By the way, when you have something like this, when it's a constant up here and trying to break it down like this, the a and b are always going to turn out to be negatives of each other. Whereas if I had like a linear function of n up top, then it would play out differently. All right. So any questions about how this partial fraction decomposition was arrived at? So now we can treat this series as a telescopic series. So the 1/2 that's multiplying each term, I'm just going to pull it out. If this converges, we can figure out what the sum is. We can just multiply by 1/2 at the end. Okay. All right. So let's see what we get. We get 1 minus 1/3 first term. And then for the second term, we have 1/2 minus 1/4. So this is playing a little differently because as of now, we don't have any cancellation opportunities at all. And that might seem a little distressing, but it's okay. We can just keep going. What's the next pair of fractions going to be? Right? Yeah, 1/3 minus 1/5. Now we have a cancellation opportunity that this minus 1/3 cancels out with this plus 1/3. And we'll keep going. 4 minus 1/6. Down to one more, 1/5 minus 1/7. Okay, and let's see how much canceled out here. You tell me.
Everything's canceled out except 1/3. Wait, I'm sorry, 1/7 and 1/6.
Yeah, the 1/4.
What about the 1/2?
The 1/2 is
Sorry.
okay. 1/5 is gone. Okay. Now, this is n equal 1, 2, 3, 4, 5. That's how far went. So, the partial sum S5 is 1/2 times 1 plus 1/2 minus 1/6 minus 1/7. Now, okay. If we throw in one more, n equals 6, so we have 1/6 minus 1/8. We see how cancellation pattern is updated. The one's still there. 1/2 still there, and then what else do I have? 1/8. Yeah, so, but the 1/6 canceled out now. -1/7 -1/8. Okay. So. We're beginning to see what kind of partial sums we're getting. It's a good idea to maybe do 2 or 3 to see the patterns. So in general, what can we say Sn is, given that we have S5 and S6 right there?
Or 3/4.
Um,
Well, it's approaching 3/4.
yeah, but I want the formula for Sn, and then we'll jump to that conclusion.
+1.
Yeah.
And what else needs to be thrown in here?
Or times one.
Yeah, multiply the whole thing by 1/2.
Oh, yeah, that's right.
Okay. All right. Now, if we simplify this as much as we can, so 1/2 times 1.5, that is 3/4, as I mentioned earlier. Minus 1/2 over n plus 1 plus over n plus 2. Okay, so this defines our sequence of partial sums. So what happens to this as n goes to infinity?
Yeah.
Yeah, these terms are going to go to 0. So that tells us that the limit as n goes to infinity of the sequence of partial sums, yes, it is 3/4.
And you get 3/4 minus 1/2. That,
But-
that, because you took the 1/2, 1/2 out.
Yes, so I combine these terms to get 3/2. Times 1/2 is 3/4. And then so I wrote this separately from this.
Okay.
So here we have 3/2 times 1/2 is 3/4. And then I still have a 1/2 multiplying all this. So I put that down here. Yes, so I want to separate what doesn't depend on n from what does depend on n. To understand the behavior as n goes to infinity. Other question? Now, we see that the limit from both examples so far, you can see what the limit is from whatever. I've been looking at these, what doesn't cancel in the beginning. Like here we have, for these first couple of terms, we have a 1 and a 1/2. And then all that's multiplied by 1/2, and the limit came from that. Similar from a previous example, we had just this leading 1 and everything behind it was canceling. So it's tempting to look at those first numbers from the early terms that don't cancel and say, oh, the limit comes from that. But that doesn't always work. And I'm going to show you another example to illustrate that.
Sorry. No.
Now we have a sum and goes from infinity of natural log of n over n plus 1. Now, before doing anything with this, what happens to the individual terms? So forget about the series, it's just a sequence of individual terms as n goes to infinity. Yes, but what is the natural log of 1? It's 0. So the terms go to 0. So it makes you think, well, okay, there's a possibility that the sequence might converge because that's a necessary condition. You must have the terms at least going to 0. But again, like the second example, this doesn't have the outright appearance of telescopic series, where we can have cancellation. So what's a way to rewrite this series using properties of logs that would lead to a canceling pattern? Yeah, the log of a quotient is the quotient of the logs. Okay. So now we can start plugging in values of n, seeing what we get. So we have log of 1, which is 0, minus log of 2, plus log of 2, minus log of 3. So on. And we see that we have a lot of cancellation going on. Well, first of all, this is 0. And then gone. So what we see is that the third partial sum, S3, turns out to be the only thing here that didn't cancel. That's minus natural log of 4. So let's see, if you were to write out additional terms and seeing what the partial sums turn out to be, anyone tell me, you might need to do one more to be sure,
Negative ln, or no, yeah, negative ln n plus 1.
of n plus 1, because S3 gave us minus log of 4. That's the pattern. In this case, it only took looking at one partial sum to see it. So that's the sequence of partial sums. The minus natural log of n plus 1. What happens to that as n goes to infinity? It goes to minus infinity. Slowly, but it does. So the sequence of partial sums does not converge, it becomes infinite. So we say that series diverges. This is why you have to look at the sequence of partial sums to be sure as to whether it converges or not. It's tempting to say like, oh, everything cancels. Next series is summing to 0. It's really weird, but it doesn't do that. So anytime you have a telescopic series, write out some partial sums, as many as you need, to see what the pattern is for Sn, and then you treat that as a sequence. Does that sequence converge? If so, then you have the sum of the telescopic series. This sequence is limited. Questions about this one? You're doing pretty well on time here. All right. There's one other type of series that I want to introduce today. That's called a harmonic series. And goes from 1 to infinity of 1 over n. Now, as n goes to infinity, the individual terms are going to 0. So that might make you think, okay, this has a possibility of converging. what I'm gonna do is I'm gonna write out first several terms of this series, more than usual, to give you an idea as to what's happening with partial sums. So if I have 1 plus 1/2, 6, 7, 8, okay. You know what? I goofed here. I've not written anything correct, but I should have given myself more room. Okay. I'm gonna have to rewrite this. The good thing I'm doing well on time. Let's see soon enough the reason why I'm running out this many terms. We'll stop soon now. Only because I'm going to run out of room on the board again.
So much.
Okay. I swear to God, there's a reason for this. Okay.
We'll see.
Now, what I'm going to do is I'm going to write another sum of fractions that are less than or equal to what we see here. So this sum is greater than or equal to. So underneath each fraction, I'm going to write a fraction that is smaller than it, because the new fractions I write, it'll be easier to figure out what they're summing to than what we see here. And trying to express the nth partial sum is going to be pretty difficult. So we're not going to do that, but we don't need to. So what we have here, this is greater than or equal to, okay. Plus 4, 8, 8, 8. Okay, what I'm doing is underneath each fraction, I'm writing 1 over like the next power of 2. So I here I have 1/8 and 1/8 in the same, but now I'm going to move to the next power of 2, 1/16. And I'm going to write 1/16 under each one of these until I get to 1/16. Point of stopping anyway. Okay. Well, now I'm reminded, seeing we have, I'm telling you here that 1/3 is greater than 1/4. And it reminds me of what I've read. I don't know if this is true about decades ago when McDonald's introducing a quarter-pounder burger, and then A&W had the third-pound burger. And apparently it didn't sell well because people thought that a 1/3 pound burger was smaller than a 1/4 pound burger. But again, I don't know if that's really true, if it's some urban legend type thing, but it wouldn't surprise me. Okay. So now I'm going to group together fractions that have the same power of 2 in its denominator. Here we have 1/4 twice. We'll both add up to 1/2. Here I have 1/8 4 times. What does that add up to? 1/2. Now I have 1/16 8 times. That adds up to, shocker, 1/2. So what this tells me is the sum of the actual harmonic series is going to be greater than the sum of 1 plus infinitely many 1/2s. Well, if I take this, if what I have here, this, so n equals 1 to infinity of 1 over n is greater than, strictly greater than 1 plus the sum n equals 1 to infinity, starting. I need to keep myself over. I'm writing the same thing, don't worry. Greater than 1 plus sum, 1 to infinity of 1/2. Because we're gonna get infinitely many 1/2s from this whole process. What's the sum of this gonna be? If we're adding up 1/2 infinitely many times. It's gonna be infinity.
1 plus infinity.
Which is also infinity. Yeah. Yeah. Something I tell myself whatever burdens I have are lightened by just a little bit. It's like, well, infinity minus 1 is still infinity. So, but this is greater than that. So that means that the harmonic series, sum of 1 over n, has to diverge. Because its sum is greater than that of another series that can more easily be seen to diverge. So even though the terms are going to 0, they're not going to 0 rapidly enough. So the series cannot be summed. So sometimes the series you're interested in, it may be quite difficult to determine if that series itself converges or diverges. Maybe the partial sums are too difficult to work with. But as we'll see more in the future, by comparing your series to another one that is easier to analyze, like this one right here, you can figure out whether your original series converges or not. Like one of the tests for convergence we'll see later is called a comparison test, by comparing to a simpler series. Okay, so any questions about how the harmonic series was proven to diverge?
So we had one. I'm still kind of confused by this, just. So you experiment, you're basically saying that throughout the whole thing, you're showing that each portion of, or part of it is 1/2.
Yeah, or actually, yeah, each batch of terms is this will sum to something greater than 1/2. And because both of these sums are going off to infinity, if I were to keep going, I would keep having more 1/2s.
It almost seems like though the further you get along to it, it does converge somewhere though. At that point, you're just adding up a smaller decimal every single time. Like look like 1 over 1,000 plus 1 over 1,001.
Yeah, you are adding on smaller and smaller numbers.
But it doesn't feel like it doesn't seem like it would actually reach a half because the number keeps getting bigger on the bottom.
Yeah.
It's not actually staying there.
Yeah. So another way to see that this series diverges is something I'm actually going to cover next time. It's called the integral test, where this series can be compared to an integral that you can show it's infinite. But yeah, it's intuitively, it's kind of weird. And to make matters worse, I can say this will be proven later. If I have a series 1 over n to the 1 plus epsilon, where epsilon is some positive number, no matter how small it is, that series converges. This is called a p series. So 1 over n to the p is known to converge whenever p is greater than 1, strictly greater. So if I exceed one by the tiniest little bit, it'll converge. Actually, I think. Even if functions, so one, n1 plus epsilon grows slightly faster, or decays slightly faster than 1/n. And this series, where the denominators are also growing faster than n, but only slightly faster. 1/, let's start at 2 in this case. N times the natural log of n. This series also converges. We see the integral test, be able to establish that. So this has just the wrong rate of, just barely the wrong rate of growth. The denominator has wrong rate of growth. If the denominator had been growing just a little bit faster, it converges. Like right on the edge.
And so that's 1/n to the power of what?
Of this right here. Yeah, here, n to the 1 plus epsilon power. So for example, n to the 1.00001 would be an example of that. And here we have n times natural log of n. Because logarithmic functions I mentioned earlier are among the slowest growing functions you can have.
I'm still just trying to figure out how this is different than, like, for example, the Hospitality rule, where if it's bigger on the bottom, then you know it's going to convert.
Yeah.
I'm trying to feel like, cause this is not, it's not really 1/16 plus 1/16 plus 1, it's 1/9 plus 1/10. And eventually it's gonna get to a point to where it's like, if I said I was gonna give you $1 now, then I'll give you 99 cents.
Yeah.
But eventually I'm not even gonna give you any pennies. You'll never get another penny from me again.
Well,
So how does it?
they're so small,
But they're
but-
still, but they're getting smaller each number.
but they never go all the way to 0. And yeah.
But nothing's being changed to n. It's still just. Yeah.
I know, yeah, yeah, because, and for instance, if you were trying to compute this sum, say on a computer, and have it add up the numbers for you, at some point, the numbers
Right.
get so small, well, actually, the computer would declare them to be 0 because there's only a finite amount of precision. So then, it's gonna give you an answer.
Or maybe it's right.
It's not. Actually, I gotta find out what it would give in that
Me
case,
and this
but.
bad boy have been through a lot together. I trust him. He
Okay.
says it converges, it converges.
Okay. So.
Okay, why do you have the epsilon greater than the 0 at the bottom there, though?
Yeah, it only converges if epsilon satisfies this condition. If epsilon is negative, it would not.
If epsilon is greater than 0. okay.
Yeah. Yeah, but I guess, next time I cover integral test, I'll try to convince you once again. Try to convert this. That's not divergence.
I'm probably just missing something so minute that just.
Well, it is counterintuitive. Because it's difficult to wrap your head around the idea that it's not just the fact that the numbers are going to 0, but they need to go to 0 at a fast enough rate for this to work. All right. Actually covered everything into my notes for today that I had to get through. Now, I a couple options here. I can either cover a little bit more just to make things easier for the next time. So the notes are longer, or we certainly have time for any homework questions. Like, okay, yes, we do.
We figure out which one it was.
Okay. The way these homework problems work in Lumen, and you'll have similar types of problems, but the specific numbers may be different. But like if you ask me about yours, then I can still help someone else.
7 and 8.
Okay, I would need to.
You want to look at it rather than me?
Yeah, let's do that. Oh, okay, so this one is a graph and the other one is also a graph?
Yeah.
Um,
I didn't know if we were limited, look at the graphic.
you can do either one. Okay, so. One, number 7 and 8, of similar behavior. Does it give you a formula for the sequence? Or just the dots?
Yeah, I wish there was one more test, it's like in chat, it'd be awesome.
Yeah. It's like, it's like this conference.
And we're all be pressing that like 15 times.
So that's what and sine.
I did
over
that.
Great for RNG.
Okay, and what it does is gives you a graph. And plots various terms of the sequence on the graph. So first I'll explain the visual way to see what the limit is, because you can see that the terms are converging to whatever y value is here, that of course they don't give you because reasons. But it does give you y values on the rest of the y-axis. So the idea is to use the spacing between y values to find the missing y value there, where you can see the dots are converging to. So that's the non-analytical way to find the limit. Okay. Now, the other way to find the limit, use this fact when covered in Cal 1, that the limit as x goes to 0 of sine x over x is equal to 1. Now, here we're not dealing with x going to 0, we're dealing with n going to infinity. But look at the argument to sine, 8 over n, or whatever number you have, it's a different number for each of you. That argument is going to 0. So another way of expressing it is sine of something over the same something. You have to be exactly the same, goes to 1, as the something goes to 0. Whatever that something is, whatever expression it may be. Now, this expression right here is not written that way, but you could rewrite it through some algebraic manipulation, trickery, multiplying and dividing by something. You can get it in that form, figure out what the limit would be. So that's another way to work the problem. That's number 7. Number 8 has a expression involving like a square root minus something. That's so number 8. Use I did a similar problem in class. You multiply and divide by the conjugate. So you have these expressions subtracted. You multiply and divide by those two expressions added. You can simplify and figure out what the limit would be. And then you can use a graph to confirm. So that's how you get through those two problems. Yes.
I have a question on number 3 on homework 2.
Okay. First, or anything else about either these two or any other aspect of homework 1?
Is what?
Conjugate. So if you have something like the example I did in class is I had a difference of square roots, and what I did was multiply and divide by the sum of the same square roots. Now, in problem 8, as written in the homework, only one of these is a square root, but you can rewrite the other as a square root. of the thing squared. That's usually real technical, the thing squared. So, because then you multiply these out, like, because this turns out to be equal to A minus B. And that simplifies all that. Again, I've done an example in class where I use this trick. Right. Last column, homework 1 stuff. Okay, Morgan, you're on. Number 3, I guess I should look at the problem.
Yeah, it's easy. I just.
Okay. Series. Okay.
My thought process was to find AN and then just plug in infinity.
Oh, well, actually, you do want to find a formula for it, but a different kind. So, okay, what you were given was, series was,
1 or 1 plus 1/6, 1/36. Plus 1/216.
okay. All right, press it as a, well, plus dot, dot, dot. Press it as a geometric series.
Mhm.
You did, yeah.
AN equals 1/6 raised to n minus 1.
Okay.
Or is that wrong?
Repeat.
I put 1/6 raised to n minus 1.
Okay. Oh, going from 1 to infinity. That,
Yeah,
okay. Don't write it this way. Have it as a geometric series for starting with n equals 0. The formula I gave you, from a sum. So while this is correct, it's not the way you want to write it. So in general, sum of AR to the n, if it is 1 over A over 1 minus R, but only if n starts at 0. So what you can do is something I showed last time. You can carry out an index shift. Drop this to 0, replace n by n plus 1 throughout. I mean, let me guess. You tried applying this formula and it told you it was wrong?
yeah.
Okay, that's why. So,
And when's homework 2 due?
like
February 8th.
So we have some time.
Yeah, yes, yeah, you have 1 week from tonight. Okay, that's good to get a jump on things because there's always more coming at you. I should point out that, even though all semester long, you'll be given at least a week to finish each assignment once I finish that section. So far, I spent 2 days on sequences. I spent 2 days on series. I won't always spend 2 days on these things. So sometimes the dates might bunch up a little bit. I'll try not to have that happen, but yes.
Do you look at it on my paper?
Oh.
Okay. What do I do? This is my phone that I wrote for.
Okay.
So what do I do? Do I just keep this as 1? When I phone, I'm doing that.
Oh, okay. So what you do is, when you set n to 0, then in your expression, you can replace n by n plus 1. Okay, well, still a good amount of time. Other homework questions of any kind? Okay, then I guess we're out of here.
All right.
Oh, now you have a question.
Yeah, but it's good to take questions.
Okay, all right.
Please put them out of here.
Check performance and stuff, you have 8 that we could turn in late, in 1, 2.
Yeah, but there, you have 8 late passes. And if you use late pass, that good for the whole semester on that assignment. So,
Okay.
so you can have up to 8 assignments.
How many assignments are in total? Like probably like.
There are 16 homeworks. Late passes can also be used on quizzes.
Oh.
And there are 4 of those.
Okay, so you just click hit like pass on.
I believe so. I haven't actually seen the process, but yeah. But